Morning, everybody. This is a collaboration between the School of Chemistry, the School of Cellular Molecular Medicine, and Bristol Vet School. And we look at how viruses remain viable in the air. Oh. There we go. So we've learned a lot about airborne disease transmission in the past few years. We know that the viruses and bacteria are responsible, propagate between hosts in the aerosol droplets we produce when we breathe, talk, cough, sneeze. There's four main contributions to this. Particle generation. So we know that where the particles are generated within the respiratory tract will have an effect on the particle size, but also the pathogen load. We know that the particle size will have an effect on the particle movement through time and space. So we know big ballistic droplets will fall out of the air quite rapidly, and the smaller aerosol droplets will float around the room like cigarette smoke. The infected dose. So does the right pathogen reach the right tissue in the right amount to cause an infection? Some things can affect this. For example, your natural immunity, if you're vaccinated, or even if you're wearing a mask. And then what we look at in our lab is the pathogen decay. So how long does the virus remain viable in that droplet? And there's extrinsic factors like the relative humidity, the temperature, if there's UV light or disinfectants in the air, but also intrinsic factors. So what's going on inside that droplet, which is driving that loss of infectivity. This has a downstream effect on the infective dose, and this helps us plan for future pandemics, but also tackle current endemic diseases in our society. So we use a particle levitation system called CELEBS. We trap a population of droplets between two electrodes in an electrodynamic trap. We have tight control over the relative humidity and the temperature. And after an intended incubation, that could be 5 seconds or 5 hours, 5 minutes, we extract them into a collection media. So we put this collection media onto a 96-well plate with some cells in, and we can determine the infection or no infection. This is an infectivity assay. This is how we see how viable the pathogen is. And this is the kind of data that we get. So we have infectivity against time, and this is comparing SARS-CoV-2 with MHV. So MHV is mouse hepatitis virus. It's a safe surrogate for SARS-CoV-2. It's kind of what we used in the early days of the pandemic. It's a coronavirus. And this is at 90% RH. This is if you go into a pub and your glasses steam up at Christmas, or you're in a steam room. This is a very humid environment, and you can see that there's gradual loss of infectivity over time. So these droplets are starting off as droplets, and they're evaporating into smaller droplets. And they're losing water and CO2 and any solvents. And it's the non-physiological conditions inside that smaller droplet which are driving that loss of infectivity. When we compare this with 40% RH, so this is a dry environment, a bit like in an office space. And you see there's a rapid loss of infectivity within the first 5 seconds of particle generation, which kind of remains constant over the 5 minutes. So these droplets are completely drying to a particle which is salt crystals and organic matter. So it's the efflorescence of the salt crystals that's driving that rapid loss of infectivity. So the MHV was an appropriate surrogate for SARS-CoV-2, this variant of SARS-CoV-2. And what I've shown you here, this was in DMEM. So this is the kind of growth media what we harvest the virus in. And it's kind of it's a representation of respiratory fluid. It's not the whole picture. It's lacking some complexity, and some of that complexity was recommended that would affect the infectivity was mucus. So what levels of mucus would affect infectivity? So we added clinically relevant concentrations of mucus to the aerosol droplets. So 0.1 weight per volume is kind of like a normal mucus production. 0.3, 0.5 is what you'd expect with disease state like COPD and asthma. And you can see there's a reduced loss of infectivity at these higher mucin concentrations. This is after 30 seconds. after 2 minutes, and then after 5 minutes, there was no difference in that loss of infectivity. So this is a transient process where the mucin is protecting the virus from the loss of infectivity we'd expect to see because of that efflorescence event. So what's going on inside the droplet? So we use similar technology, CKDB. So we levitate just one droplet, shine a laser on there, and then from the scattered light, we can determine the morphology and also the radius of the droplet. And we get an evaporation profile. So we see that this is DMEM with no mucin. You see there's a homogeneous evaporation to the point of efflorescence where this particle is dried, and this scattered light is a kind of characteristic of crystal amorphous morphology. When we add mucin concentration, you see there's a heterogeneous evaporation profile where we get this kind of inclusion formation. So it's a bit like an emulsion or like a oh God, what are they called? Like a snow globe that you shake, and you get this kind of emulsion in there. And this is some SEM of the kind of the image of the droplet, a dry droplet. Okay. So what I've talked about is all at low RH, so dry environments. I'm going to talk really quickly about what's happening at humid environments. So our droplet, respiratory droplets contain sodium bicarbonate. It's the natural buffering system for CO2 in the body, in saliva and in blood. And in the air, the CO concentrations are 440 parts per million. The CO2 we breathe out is 38,000 parts per million. So as the droplet evaporates, the CO2 is moving from this high concentration to a low concentration. The CO2 is taking away acidity from the droplet and making the inside the droplet more alkali and increased concentration of salt. It's driving this chemistry equilibria inside the droplet, making the droplet more alkaline and increased concentrations of organics and salts. So this has kind of been reflected in other groups' work where they model respiratory droplets and they show that these droplets move to high pHs. And what does that mean for the virus? So this is MHV, and with SARS-CoV-2, we see this loss of infectivity at higher concentrations, at higher alkaline concentrations. So we propose that the high pH is driving that loss of infectivity in the more humid environments. So a bit later on in the pandemic, we got our hands on the different variants of concern, and then we see that as the virus has evolved, they kind of lose. They kind of become more susceptible to high pH. So this phenotype was selected for as the variants evolved over time. And this susceptibility at high pH was really reflected in the aerostability. So as you can see, the original and the Delta variant, so aerostability was selected for over time as well. So the variants had different high pH aerostabilities, and the survival at higher pH was a good indication of its aerostability. So in conclusion, there's kind of two mechanisms of decay here. So we've got the rapid loss of infectivity at low relative humidity, 40%. That's the efflorescence driven decay. There's different decay profiles for different variants. So the original was less susceptible. But there's other contributions, for example, the internal composition of the droplet and atmospheric conditions. Now we're moving on to what about other respiratory pathogens. So over the past year, I've built my own Celebs instrument that we're going to start to look at different bacteria species, pathogenic bacteria species. And yeah, I think that's about it. So I want to thank everyone associated with this, and thank you for Salome at Dyson for looking after me on my placement, and Zhang Han, who helped me with the CKDB measurements. yeah, thanks for listening.